Our car battery has internal resistance of 0.060 ohm. It is recharged using a battery charger having an EMF of 14 volt and internal resistance of 0.010 ohm as shown in figure 6.1. So the first thing that you need to understand, when the battery would be charged up, this will be the dominant source, and this will be the dominated source, if that's a good word for this case, which means that in this entire circuit, this one will have the higher voltage, this EMF of this battery will be the lower voltage. So current will be practically flowing through this direction, and that will recharge up the battery. That will reverse the typical reaction which produces electrical energy. So in this process, electrical energy will be stored within the car battery as chemical energy. That's a recharging process. That's applicable for any rechargeable battery, cell phone batteries, or remote control batteries, or any type of rechargeable batteries, power banks. They all work in this mechanism. We have to apply a voltage that is slightly higher, preferably slightly higher than the EMF of the cell. If we apply a very large voltage, the process will be very fast. But if we apply a much faster process, that will heat up the battery because of the internal resistance, and also heat up the charger because of its own internal resistance. So both of your components are going to get heated up pretty fast. You're going to have the charging process happen pretty fast, but at the same time, it will be heated up. That might lead to cause to some sort of danger, trouble, and also this will definitely significantly lower the lifetime of your battery's useful cycle. That's why fast charging is not always recommended, but even whenever you need fast charging, because our life is pretty fast right now, so fast charging can be used, but shouldn't be used all the times. Anyway, let's have a look at these questions. At the beginning of the recharging process, the current is 42 ampere, and the EMF of the battery E measured in volts. For the second infused sequence, the magnitude of the total resistance. This is pretty simple. You just write 0.160. That's it. The total EMF in the circuit, give answer in terms of E. Total EMF in the circuit, you can write E minus 14, or you can write 14 minus E. If you ask me, I would definitely prefer to write 14 minus E, because I do understand that 14 volt would be the larger EMF and E would be the smaller EMFs. That's why I'm preferring this version. And I do understand that current will be flowing in the clockwise version. Let me write this at I, whatever. Use your answers in one and data from question to determine the EMF of the car battery at the beginning of the recharging process. So the question says that at the initial case, the current was 42 ampere, and we also have the whole, we have to also have the resistance of this whole circuit. So we can essentially apply Kirchhoff's second law for this whole circuit. We don't have any specific sequence over here, so you can pretty much start from this corner and go in a clockwise pattern like that. So I'm assuming the current is happening to the right. So I can write I into 0.060 plus that same current will be flowing through this battery at this source as well, 0.10. Bit smaller thickness might be helpful. Okay, 0.10. This is the potential drop equals to 14 minus E. And in the place of I, you place 42. So 42 into 0.160 equals to 14 minus E. If you do the whole calculation from this thing, you can find out the value of E. Have a calculation and still tell me how much do you get from here. Eta kore amake bolo koto ashe.
7.3 volts.
The EMF of the battery becomes 7.3 volts. Okay, so eta gelo. And then this next page is this one. Where did the earlier page go? Oh, it got overlapped. Never mind. I just learned this insert PDF option very recently. I find it pretty helpful for the worksheet solution process. In B number option says that for the majority of the charging time for the car battery, I mean, because we might have to take some reference. For the majority of the charging time of the car battery, the EMF of the car battery is 12 volt and the charging current is 2.5 ampere. So it's saying that for the majority of the case, which means whenever we connected the circuit the first time, the moment we closed the circuit, the EMF of the battery was very low. It was 7.3 volts, which means it was pretty much drained altogether of its energy. That's why the initial current was 42 ampere. This is the initial current at the beginning of the recharging process. But for the gross time or the significant amount of time, the car battery had the average current was this one, and the car battery had an effective EMF of 12 volt. So the battery is charged to this at this current for 4 hours. Calculate for this charging the charge that passes to the battery. This is very simple. Q equals to IT. So you just write 12.5 multiplied by 4 hours, 4 into 3600. That's the amount of time in seconds. You just calculate this and give this number in standard form if required. The energy supplied from the battery charger, energy supplied is given by E equals to PT power into time. Power in this case can be given by V into I into T. This V would be the voltage supplied from the battery charger. So the battery charger voltage was 14 volt. So 14 into 12.5, that is the average current, multiplied with the same time. So 4 into 3600. That is the whole thing. If you don't want to do it in this manner, I actually VIT, if you don't want to use power into time, you can also alternately you can also calculate this equation in terms of E equals to VQ from the definitive equation of voltage. Energy equals to voltage into charge. You just calculate the charge from here. So you can place the voltage 14 volt over here and place the value of the charge from this equation, and eventually you will get the same answer as well. Either of this method can work. This is an independent method without this question. This is a dependent method using this value. So তোমাদের যেটা মাথায় আসে যেটা ভালো লাগে সেটা করতে পারো. In number 3, it says the total energy dissipated in the internal resistance of the battery charger and the car battery. The total energy dissipated in the internal resistance of the battery charger and the car battery. So how much energy was wasted? So we can very easily calculate this by the energy lost. So in this case, I can write E equals to I square into the total R. So I'm going to write this as, let's say, R total into T. So this is basically the total power due to the resistance. So this is the amount of power that be wasted. If you multiply that by T, you get the total energy dissipated. So in this case, current was 12.5. So 12.5 squared. The total resistance of the circuit was calculated over here, 0.160. Multiply by that time, 4 into 3600. So you get this calculation and calculate how much energy was wasted in terms of heat energy. Now C says, using answer in B, calculate the percentage efficiency of the transfer of energy from the battery charger to the stored energy in the car battery. So use your answers in B to calculate the percentage efficiency of transfer of energy from the battery charger to stored energy in the car battery, which means basically you're trying to find out the efficiency. So what we did over here, we calculated how much energy was provided from the charger. We calculated over here how much was wasted. So let's say this was energy, input energy, and this is the wasted energy, and you're trying to calculate the efficiency. Efficiency formula is pretty simple. Efficiency is given by what? Useful energy divided by total energy, or I can write input energy, which can be given as useful energy can be obtained by the subtraction. So I can write input energy minus wasted energy. This is the total amount of energy that got useful, got into the battery, divided by the input energy. So that ratio gives you the efficiency. Essentially, you can multiply by 100% because the question is asking in percentage. So that gives you the value. এই প্রসেসটা বুঝা গেছে কিনা?
Yes, sir.
আচ্ছা, up so far কারো কোনো question? Anyone? No, apparently. Okay, let's try and go for the next question. Have a look. I wanted to describe this question to give you an idea that how does the charging process actually works, and the idea of heating effect with this thing and not. So if we want to do the charging process pretty fast, we have to risk for heating effect. If we want to charging process slowly, then the battery will not be heating up, and you would have a much safer charging process, and the longevity of the battery will be longer as well. And these questions are actually pretty simple. We have solved quite a good number of questions in between. That was a very early question, number 6, which I didn't discuss earlier. So I wanted to pick it up, solve these as well. But we solved this one. The emitter question we did solve. This is something similar to earlier, so I'm not solving this. You can try this, and if you can't, I'll help you. There is a graph question that I'm really interested in, which I am trying to look for, where you have to draw. So there is another question for the similar process. Only in this case, we are not doing any charging. One of the batteries is 12 volt, the other one is 3 volts. So you do understand whenever current will flow, current is going to flow out in anti-clockwise direction, because this battery source is going to overpower this battery source. This has a smaller EMF, this is a bigger EMF. So basically, in the process of current flowing through this circuit, this will be draining energy, which means this one's chemical energy would be reduced, and this will be gaining energy, which means this one's chemical energy stored would be increased. Obviously, there will be some heat loss due to the 3 resistors that we can see in the circuit. So that is the whole thing. And depending upon those concepts, we have some calculations over here. You can attempt this. If you get stuck, I might help you later. I'm interested in number 26. 26 আমাদের কিছু graph আঁকা লাগবে, and we have 2 set of graphs we have to draw, and we have to understand their content pretty minutely. So keep your eyes peeled and try to understand what I'm saying. Just a second, I have a call from the office. আমাদের নতুন কোচিং অনেকে খুঁজে পাইতেছে না, so I have to guide people to reach there. Anyway, I'll silence the phone. Okay, got it. So এখানে আমরা এই 26 নম্বর কোশ্চেনটা দেখি। A variable resistor is used to control the current in a circuit as shown in figure 5.1. So we have a source, we have a current coming out, and emitter is connected over here. This is a fixed 6 ohm resistor, and there is a variable resistor. From the position of this variable resistor, you can see over here that if you move the slider to the left, the total resistance of the circuit will be less because current only have to flow to the left part of the variable resistance over here. So current will enter through here, flow through this part, and eventually get back to the battery. So if you move the slider to the left, there will be less resistance. If you move the slider to the right, there will be more resistance. এই পার্টটাকে বুঝতেছো কিনা আগে দেখো. Is this part clear? The position of the slider will control the total
Ji,
resistance of the
sir.
circuit. Okay, this is the first thing. And then the question says the variable resistor is connected in series to 12 volt power supply of negligible internal resistance, an emitter, and a 6 ohm resistor. The resistance R of the variable resistor can be varied between 0 and 12 ohm, which means this one has a minimum resistance of 0 left position and maximum resistance of 12 ohm on the right. The maximum possible current in the circuit is 2.0 ampere. Calculate the minimum possible current. The maximum possible current in the circuit is 2.0 ampere. Maximum possible current will happen for the minimum resistance. Minimum resistance is possible when this variable resistance have 0 ohm, which means 12 by 6 gives you 2.0 ampere, which makes sense. What is the minimum possible current? Minimum possible will be happening for the maximum resistance. That is when the slider will be placed all the way to the right and the entire resistance of the variable resistance would be included in the circuit. So in that case, the total resistance of the circuit would be 12 ohm plus 6 ohm gives you 18 ohm. So this value should be what? বলা ওই ভ্যালুটা কত হবে? Holy shit. My bad. I shouldn't have said that.
0.67 amperes হবে.
Okay, আচ্ছা ঠিক আছে। যদি আমি পুরো ঢুকাই ফেলছি, it's a good thing. You can simply drag and drop and actually work through it. আচ্ছা ব্যাপার না। ঢুকাই যেতে ফেলছি, so কোশ্চেন বাই করি, সমস্যা নাই। This will be 12 divided by 12 divided by
So 18.
18. So this will be 12 divided by 18. তোমরা কি গ্রিন দেখতে পারতেছো সবাই নাকি আমি ব্ল্যাক ইউজ করব? আমি রেড ইউজ করতে পারি if you want.
ঠিক আছে।
আচ্ছা 0.67 ampere. Then the question is on figure 5.2, sketch the variation with R of the current I1 in the circuit. Now have a look. This current over here in this circuit, this was labeled as I1. So they have named this current I1. So on figure 5.2, sketch the variation with R of the current I1 in the circuit. So when the resistance will be 0 and as the resistance will increase from 0 to further, the current will drop from 2 ampere is going to drop all the way up to 0.67 ampere. What we are asked to draw is for a graph, and you can see over here for the graph we have a 2 marks over here, and they have given some gradation over here for 4, 12, 4, 8, 12, and then comes something else. This is supposed to be what? 16, and we do not have 16 ampere. Do we have 16 ampere? 6 plus 12. What is the maximum resistance? Maximum resistance was 18 ohm. So 4, 8, 12, এখানে কত হওয়ার কথা? 16 হওয়ার কথা না?
Ji, sir. 16 হওয়ার কথা।
ভ্যালুটা দেয় নাই, but you have to understand that within the same scale this is supposed to be 16. So they haven't actually given us the graph all the way up to 18 ohm. So it means the last value is not going to be 0.67. So we have to practically calculate by the same formula that we have. So 12 divided by total resistance, we have to calculate the current by this variable formula for the individual value of these I values. So try to understand, when the variable resistor has a resistance of 4 ohm, the total resistance should be how much? I mean, the current value can be given by this equation. Let me just simplify it. 12 divided by 6 plus R. This is the equation. ঠিক না? দেখো এই ইকুয়েশন বুঝা যাচ্ছে কিনা?
Yes, sir.
সো তোমরা যেটা করবা প্রথমে 12 divided by 6 plus 4 করলে হচ্ছে 1.2. So this is going to be 1.2. This is 1.0. So this would be our first point right over here. Let me zoom in this for easier drawing. So one of the point would be over here that we know, and second point would be here. Then 12 divided by 4 plus 8. 12 by 14 করলে কত হয় দেখো তো? 0.86. So over here this will be 0.86, which means you can draw it at in between 0.8 and 0.9. So 0.8 and 0.9 are in between somewhere over here. Then if you consider 12 divided by 6 plus 12 means 12 divided by 18, which is 0.67. Acha, it actually how possible now. I'm sorry. I'm really sorry. This is actually not possible because this scale was not for the total resistance. This one for the variable value of R. The value of variable resistance R is only changeable from 0 to 12. This one can have a minimum resistance of 0 ohm and maximum resistance of 12 ohm. This is mentioned over here. So the graph will not be extended over here. The graph will finish over here. I was mistaken. This was not the total resistance. Forget about this value. Or forget whatever I said over here. বুঝছো কি বলছি বলবান? I was mistaken. ভুলটা কথা করছি বুঝছো? I assume this was the total resistance, but this is not the total resistance. This is supposed to be the part resistance. So this was a bit of mistake on my part. So then at 12, this is going to be 0.67. So let's find that out. This is 5, this is 6, this is 7. 0.67 is about 2/3 height. So now you got 4 points, and try to do your best to draw the smooth curve through these points. If you label these points by dot circle, the examiner will definitely give you the mark, because the examiner would know that you know your thing. And then try as best as you can to draw the as smooth curve as you can. Preferably try to keep your wrist somewhere around this place. Try to keep your wrist somewhere over here so that you can have a smooth hand motion like that, and then you draw this curve by multiple try. So এটা হয়ে গেল এই গ্রাফটা গেল, and then number B, we're going to see for number B. Number B says the variable resistor in A is now connected as a potential divider as shown in figure 5.3. So now we have connected the ammeter in the lower section of the circuit, the new section of the circuit, and this current is named as I2. Calculate the maximum possible and minimum possible current I2 in the ammeter. Now, this is something that you really have to understand. Have a look. This is the potential divider circuit where this position of the slider will be dividing the voltage that will be available on the left and the right. So what I need you to judge, you have to remember that a potential divider or a rheostat actually has a very long resistance wire that is coiled like that on a non-conducting cylinder, and we move a contact so that certain part of the wire actually becomes a part of the circuit and not. So the position of the slider is going to produce a voltage drop over here, and the remaining voltage will be applied up to here. And this position will determine how much is this going to be and how much is this going to be. But the sum of this total voltage caused by the entire thing is going to be 12 volt anyway, because the question said that the source have negligible internal resistance. So the total EMF of the supply will be available across this whole long resistance. So if we move the slider, so have a look. The question says calculate the maximum possible and minimum possible current. You're going to get maximum current across through this branch whenever you have maximum voltage across these 2 points. So have a look. This point, let me draw that with the green maybe, across this point and the contact point of the slider. That is possible if we slide this slider all the way to the right over here. So for this position of the slider, we're going to have max voltage, which is going to give us max current. And vice versa, if you push the slider all the way to the left, we're going to have 0 voltage and the current is going to be 0 ampere. So you don't have to show the current for minimum. You can simply write 0 over here, and that's good enough. Examiner is going to give you the mark anyway. And as for the maximum current, you just have to do show a little bit of calculation. 12 divided by 6 equals to 2.0 ampere. And you just write 2.0 over here. বুঝে গেছে কিনা বলবান?
স্যার ঠিক আছে।
এটা পজিশনের উপর বেস করে চেঞ্জ হচ্ছে। Then it says the sketch on figure 5.4 the IV characteristics of a filament lamp. আচ্ছা, এটা তো একটা হাবিজাবি জিনিস। এখান থেকে আমাদেরকে একটা ডিক্রিজিং গ্রেডিয়েন্টের গ্রাফ আঁকতে হবে। You don't have to finish it all the way. You can just finish it over here. No big deal. You don't have to finish it all the way to the right side. But it should have a decreasing gradient and Allah. Okay, so this is the IV characteristic for the filament lamp. And then number 5 says, and 5C2 says, the resistor of the resistor of resistance 6 ohm is replaced with a filament lamp in the circuits of figure 5.1 and figure 5.3. State an advantage of using the circuit in figure 5.3 compared to the circuit of figure 5.1 when using the circuits to vary the brightness of the filament lamp. এই কোশ্চেনটাকে ভালো করে বুঝো। The resistor of resistance 6 ohm is replaced with a filament lamp, which means currently we are supposed to judge that this one is replaced with a filament lamp. So consider there is a filament lamp over here. আমি ক্লাস নিতেছি, একটু পরে কল দিই। হ্যাঁ, হয়েছিল কাল রাতে ভাই, তারপর ভাইয়ের সাথে কথা বলছি, একটু পরে কথা বলি। আচ্ছা। sorry. Okay, so it says that the resistor of resistance is replaced for in the cycle sphere 5.1 and 5.3. So we are replacing this thing over here with a filament lamp, and we are also replacing this one as a filament lamp as well. Both of these circuits are replaced with filament lamps. 6 ohm resistor is replaced with a filament lamp. The question is asking us, try to understand. I'm going to keep those circuits in vision. Yes. The question is asking us, state an advantage of using the circuit of figure 5.3 compared to the circuit of figure 5.1 when using the circuits to vary the brightness of the filament lamp. So, state an advantage of using the circuit in figure 5.3. What is the advantage of this one over this one while controlling the brightness of these two bulbs? Can anyone think of some benefit that you can talk about? What could possibly be the benefit of this thing? I'll give you a small hint. For both of these circuits, the maximum current is 2 ampere, maximum current is 2 ampere, which means maximum brightness of the bulbs will be pretty much the same. Have a look at the minimum current. This circuit gives you 0 minimum current, whereas this circuit gives you 0.67 minimum current. This circuit does not practically completely switches off the bulb, because whenever you're going to set the maximum resistance, the bulb is still going to have 0.67 ampere of current. Do you understand this point?
Ji, sir.
At the maximum value of the variable resistor, there will be still some current remaining within the circuit, which means for this circuit, your bulb can never be completely shut off. It will have minimum resistance, minimum brightness, but it cannot be shut off. But for using this circuit, you can completely shut off the bulb. You can achieve 0 ampere. That is the practical benefit that I can think of. However, using both the circuits, we can control the brightness, so there is no big deal. Both of them are capable to do the brightness control, but one can ultimately shut off the bulb, the other cannot. এই হচ্ছে ডিফারেন্স। বুঝা গেছে কিনা? লবান বুঝা গেছে? I think so.
Ji, sir.
আচ্ছা, এখানে আসলে খুব ভেজালের কিছু নেই। এই কোশ্চেনটা তোমরা নিজেরা ট্রাই করবা পুরোটা। I want you guys to try this on your own, at your own effort, and if you can solve this, I'll definitely help you for this one, no problem. If you haven't already, you should try this on your own. আচ্ছা, এটাও খুব সিম্পল কোশ্চেন টু বি অনেস্ট। এরকম কোশ্চেন আমরা এমসিকিউতে একটা করছি। Let's try number 34. Have a look. Question 34 says a circuit used to measure the power transfer from a battery is shown in figure 4.1. The power is transferred to a variable resistor of resistance R. 34 নম্বর কোশ্চেনটা টার্ন আপ করো, সবাই ওয়ার্কশিটে দেখো, তোমাদের ওয়ার্কশিটে দেখো, পরে আমি যখন কাজ করবো তখন ওয়ার্কিং দেখো, সমস্যা নেই, কারণ এখান থেকে অ্যাকচুয়ালি এই লেভেলের ফন্ট সাইজ পড়া খুব ডিফিকাল্ট হওয়ার কথা তোমাদের ভিডিওতে, স্পেশালি ফর দোজ হু আর ইউজিং এ সেলফোন ডিভাইস। পিসিতে অ্যাকচুয়ালি পড়া যায়, বাট সেলফোন ডিভাইসে এই ফন্ট সাইজ পড়তে গেলে খবর হয়ে যাওয়ার কথা। এনিওয়ে, a circuit is used to measure the power transfer from a battery is shown in figure 4.1. The power is transferred to a variable resistor of resistance R. Okay. The battery has an alternating force EMF E and internal resistance R. There is a potential difference PD across R. The current in the circuit is I. By reference to the circuit shown in figure 4.1, distinguish between the definitions of EMF and PD. By reference to the circuit shown in figure 4.1, distinguish between the definitions of EMF and PD. So how would you write this in terms of this circuit? I'm not sure what the mark scheme holds. I actually forgot. It's been a pretty long time since I last solved this problem. But this is how I would write this answer. EMF is the amount of energy consumed by each coulomb of charge to go across the entire circuit and back to the cell, and also to pass through the cell itself. So I'll say this again. EMF is the total energy consumed by 1 coulomb of charge to pass through the entire circuit, including the battery itself. মানে হচ্ছে তুমি যদি মনে করো, let's say if I want to show you this in a magnified version, let's say you have plus 1 coulomb charge over here. Actually, positive charges never move, but all of our definitions and hypothetical and conventional they are all based on positive charges. So that's a mess that we have to deal with, or you have to remember that this is not true, but we are learning it like that. So the idea is that if you I can actually go for the electron. Let's say 1 coulomb of electron comes out of this negative end, goes to the entire circuit, and enters to the positive end, and then they pass through the whole battery and eventually comes back to the same starting position right over here. The amount of energy that would require to achieve this movement to the entire circuit, including the battery, that is the EMF. The amount of energy that the battery provides to 1 coulomb charge to make one complete travel across the whole circuit, including the battery, is defined as EMF. Do you understand my point? This is the theoretical definition. I'm not still using the circuit. I'm just telling the theoretical definition. And potential drop, on the other hand, essentially means the difference of potential across 2 points of a circuit. So you would have some potential drop maybe across these 2 points. Well, this is not actually possible because this resistance is actually inherently over here. This is just a easy way to represent the battery. The potential drop is basically the potential difference across 2 points. For example, what is the potential difference across the two resistors over here would be given by this voltmeter. So whatever the amount of energy that the battery gives out, all of this thing would not be used as potential drop. You know this concept, that terminal voltage and is one thing. There is a little bit of loss voltage for every practical battery. And as a result, EMF is never used completely for any circuit. The battery always consumes some amount of voltage of its own to overcome its own resistance. So that's what we define as loss voltage. So once again, getting back to the question actually was asking us that by reference to the circuit shown in figure 4.1, distinguish between the definitions of EMF and PD. So what I'm going to write, for the circuit, comma, EMF equals to I into capital R plus I into small r, and PD equals to I into capital R. I'm only going to write these two equations, and let's see what the examiners think about it. So this is how my answer is going to look like. EMF equals to I into R plus R, PD equals to I into R. I'm not going to write anything else. And I'd like to have a shot at the mark schemes to see what the mark scheme holds for me. Let's have a look at the mark scheme. This is the very last question. So it should be easy for us to get to there. Boom. And yay! No. Chemical energy to electrical energy, PD equals to electrical energy to thermal energy, idea of per unit charge. So why did they use the idea of this circuit? Am I missing out something? What number question is this? 34. 34. EMF equals to chemical energy to chemical energy. Okay, good. PD equals to electrical energy to thermal energy. Good. Idea of per unit charge. Many statements were based on general statements and regarded as EMF and potential difference. Consequently, there are many references to other forms of energy, other energy changes driven to the given circuit. What is the given circuit?
Sir,
So
conversion
measure
of
the power transfer
energy.
of battery shown. The power is transferred to the variable store. The battery is the potential. আচ্ছা বলো. I'm not going to score any mark on this question if I have only these two equations, to be honest. I'm not going to get a single mark. I'm going to get 0 over here. This is not incorrect. This is just inappropriate or unexpected or not the expected result answer of this question. Bolo.
Sir, how will we know we have to talk about conversion of thermal energy in the description of PD
You don't.
in this question?
You don't. And that's the risk that you have to overcome. And
And sir,
that
we will write
and
everything.
your and let me clear this out. It's very hard rendering and this is very bad. Is that there is no way you can know what specific aspect of this thing that the examiners are looking for. For example, I was thinking about in terms of this circuit, so I use the variables shown in the circuit to write this thing because I highlighted on the term by reference to the circuit. But they use no reference of the circuit in this question whatsoever. Neither did they say that this variable resistor is actually a heating element. This variable resistor is a variable resistor, but this could as well be something else. Electrical energy will be converted to heat. Yes, I understand that. But mentioning the energy transfer is the key idea. They could have said by reference to the energy conversion in figure 4.1, distinguish between the definitions of EMF and PD. They could have said that, and that would be a perfect mark scheme. But the mark scheme that they have provided is not essentially, in my opinion, it is not essentially congruent to what they are asking in this question. So if you ask me that how would we know? Well, the answer is you wouldn't. You will do this mistake. For example, I made this mistake. So a lot of other kids would also do this mistake, and this will come out as a differentiating line between people who made a lot of practice and knew this kind of BS questions, or people who didn't do a lot of practice but they're good on their concepts and didn't score this mark?
Understood, sir.
I'm sorry to tell you this. I understand this is not a good way to, or at least, what can I say? At least a honorable way. Honorable is not a perfect word. I mean, it's not a very, what can I say?
No, sir, you said the right thing that we have to practice, right, sir? Now, or else, how will we know?
Exactly. There is no way you can guess what will be the correct form of this kind of answer, because you can see that the question is asking us one thing and the marking is providing us a totally different thing.
Yes, sir.
So there is no way you can actually guess that. I couldn't. Been teaching CIFs for a pretty long time, but well, you see that, I mean, I solve this question, let's say every once a year when I solve the electricity chapter, and maybe I have the exact same reaction every year, but this year is getting recorded and gonna be uploaded to YouTube. That's the difference. So you can figure it out. Question number C. The variation with current I of the PDV across the R is shown in figure 4.2. So we have a linear decrease. So the voltage is not starting from 6, it's starting from a very slightly less than 6. Whereas the question actually does the question say that no, the question doesn't say us anything about the starting area. So okay, use figure 4.2 to determine the EMF E. So the EMF E would be the very value over here. This one. Hold on just a second. Assalamu alaikum. Yeah, I'm trying to parcel. Okay. So you can see that when the current is zero, when I is absolutely zero, this is the x-axis. This is the point where you're gonna have the EMF of the battery. When there is no current, so there is no loss due to the internal resistance. So you have to precisely read off what this value is. Do not write this as 6 because this is not 6. So I'm gonna zoom in and let's have a look what value this is. So what is the value of this starting point? Y-axis value. What is the y-axis value?
5.8.
5.8.
Agreed. 5.8 is the correct response. Good. So I'm going to write over here 5.8. What is the internal resistance? How can we calculate the internal resistance out of this circuit? There's a 2 mark in this thing, so you might actually wonder that, well, there has to be some sort of calculation involved. It's actually quite easy if you ask me. I'll show you how. You can choose any value on this graph, because let's say this is the terminal voltage, right? This is the voltmeter reading. So this is the terminal voltage. So you can see if I choose 4 volt, I'm choosing 4 volt because I can see there's a very good crossing over here. I mean, through this point, the line is actually going through this point very vividly. I mean, compared to this point or compared to maybe this point, they are somewhere on the halfway of the box, but this is a very good cross point. So if I take these two values, terminal voltage V, 4.0, current is 2.0. So I can write this equation, E equals to 2.0 into, what is the resistance of this external resistor? Oh no, this is a variable resistor. So hold up. Sorry, I actually messed up the equation. I'm going to rewrite this. Sorry. So whenever we have a current of I 2.0, I can write that the EMF of the battery, which is 5.8, which we just decided, equals to the terminal voltage. Sorry, equals to the terminal voltage. Let's say capital V plus loss voltage small v. So I can reform this equation as 5.8 equals to, here the terminal voltage is 4.0 and the current was 2.0. I'm going to write this, and the internal resistance is something that is unknown. So you just have all the things in numbers. So you just replace these values and you get the answer. Kids, do you understand how did this equation get into existence? এটা কি বুঝছো? এই পুরো ইকুয়েশনটাকে বোঝা যাচ্ছে কিনা দেখো। এটা হচ্ছে একটা উপায়. This is some value that I chose. If you want to work with some other value, let's say if I want to do this for a different value, I just have to find out, sorry.
স্যার কারেন্ট 2.0 কিভাবে?
এই যে sorry 1.0. হ্যাঁ thank you. My bad. বলবান ভুল বলছি. 1.0 কারণ 1.0. I need to erase this, so let's just delete this and right over here. If you want to go for a different set of answer, let's say I'm going to do this now with red. And let's try to find out another good cross point on the graph. If we want to do pattern this for a different graph, I can see that this is a very good cross point. Do you see this point, Polaman? This one. So I can see that for this point, the current would be for this point the voltage is exactly terminal voltage is 2.0 and the current is 2.1. So I can also write 5.8 equals to 2.0 plus 2.1 into R. Can somebody tell me the value of these two equations? এখান থেকে R এর ভ্যালু কত আসে আর এখান থেকে R এর ভ্যালু কত আসে? এটা থেকে কত আসে দেখো তো? 5.8 1.8 divided by 1. This is 1.8 ohm. And then 3.8 divided by 2.1. 3.8 divided by 2.1. 3.8 divided by 2.1. We got 1.81, 1.8. Up to 2SF, we got 1.8. So we pretty much get the same value. The point that I'm trying to make over here is that you can choose any point over here on the graph. Just make sure it's a good cross point. Goes through the crossing of the grids and you are good. বুঝা গেছে কি? বুঝা গেছে পোলামান?
Yes, sir.
So you have to write this equation, and what I would highly recommend that although they haven't asked you to actually give any mark on the graph, but I would recommend that whenever you are using two numbers, give small give small lines over here and over here with your pencil, so that the examiner knows that you actually use these two values. You don't have to, but if you do, it's a good thing. These are subtle hints that makes your paper more what can I say, more appreciated by the examiners. D1, using data from figure 4.2, calculate the power transfer to R for a current of 1.6. Acha. Using data from figure 4.2, calculate the power transfer to R for a current of 1.6. This is pretty simple. 1.6 হচ্ছে এই জায়গায়, 1.6 এর জন্য আমাদের ভোল্টেজ কত দেখো তো, তোমরা ইয়া থেকে দেখো, প্রিন্টার থেকে দেখো 1.6 এর জন্য ভোল্টেজ কত আসে? 1.6 এর জন্য ভোল্টেজ আসে হচ্ছে 2.9. Am I correct? 2.9 ভোল্ট হয় কিনা দেখো।
জি স্যার 2.9 আসে।
এটা ক্যালকুলেট করে দেখো কত আসে। 4.64 watt. So you just write that over here. Then the question says that using your answers from C1 and D1, calculate the efficiency of the battery for a current of 1.6 ampere. So this is the key, beautiful question. Using answer from C1 and D1. So in C1 we got EMF, and in D1 we calculated the useful power. So the output, the total power which was drained from the battery can be given by, have a look, just show answers one thing. This is the equation for power. This is one of the expression for electric power. This voltage could be any voltage. So if we want to find out the source power, that what is the power drained from the source power can be written as P equals to EMF of the source into current. What is the useful power? Useful power can be written in terms of P, let's say useful, equals to the terminal voltage into current. Do you see what I'm doing over here? It's the same expression, one written for the battery and one written for the resistor. So if we're trying to find out the efficiency can be given by VI divided by EI. II crosses out anyway. So you get the voltage over here. What is the voltage? As EMF is 5.8. This is good. And for this case, whenever the current was 1.6 ampere, the voltage was 2.9. So this is 2.9. I think this is perfectly 50%, right? ঠিক আছে? আমি কোথাও ভুল করছি? 29 দুগুণে 58 হয়? হ্যাঁ, 25 দুগুণে 50, 4 দুগুণে 8, ঠিক আছে। এটা বুঝা গেছে কিনা বলবান দেখো, বুঝা না গেলে কোশ্চেন করো। হ্যালো,
জি স্যার ঠিক আছে।
আচ্ছা, এই পর্যন্ত আমাদের ওয়ার্কশিট শেষ। আর ওয়ার্কশিটগুলো হচ্ছে W13 পর্যন্ত কম্পাইল করা। সো প্র্যাকটিক্যালি স্পিকিং তোমরা যদি আরো ফার্দার প্রবলেম সলভ করতে চাও, recent years থেকে backward try করতে পারো. If you want to attempt really challenging questions, I highly recommend that you first attempt the March session questions, February, March, the small m variants. This variant only happens in India, so typically the difficulty of these questions are a little bit more than regular May, June or October session questions, because the kids are pretty good, and obviously they also experience the same scaling thing, so the examination process is very much standardized. But if you are looking for good problems, slightly more difficult than regular problems, attempt the February, March session first, and then you can do all the other sessions as well. And if you get stuck into something, we can talk about those things in a later class. That's pretty much it for the electricity chapter, for our discussion of lecture, theory, and problem solving. At this point, we're going to jump into atomic physics or radioactivity class notes. We have that class notes attached in our booklet, I believe. I'm going to have a look at it. Radioactivity notes, please be there. Yes, we have it over here. Okay, what I want you kids to do is pull this up and start reading from here up till this much. This is the part of the whole discussion that was included in your O levels. I want you to read the first full page and up to this much. And comparison between the different ionizing radiation, you already know this thing, the alpha, beta, gamma differences, what are those differences between them. This is also something that I'll not discuss in detail unless you ask me certain questions. So এই পর্যন্ত পুরোটুকু পড়ে আসো. I'll give you some 5-10 minutes and then I'll be back. বুঝছো কি বলছি? বলবান
জি স্যার।
এটা পড়ে আসো, এখান থেকে পড়ে আসো, তারপর আলাপ করতেছি. Pause in the recording. এখানে within this part, this is the basic description for alpha particles, and from we have the observation, also the decision over here. And one thing you have to understand that the Rutherford's alpha particle scattering experiment, or we call it by Geiger-Marsden experiment as well. This experiment does not give us any idea about the shell structure of the electron. It only gives us the idea that inside the atom there is a very tiny, very massive, highly positively charged nucleus. That's the decision that we can get from this experiment. The shell structure of electrons was proved by other experiments later. Scientist Thomson was responsible for most of the experiment. However, the structure was given by Niels Bohr. So that's a different story. The Rutherford experiment gives us the idea of nuclear atom, nothing about the electrons. You shouldn't confuse this. Important information. The second thing that is important is that radioactivity decay has three aspects of its randomness. You have to be able to distinguish these three things because they can be quite synonymous. I mean, the third one is easily rememberable. Third one, you cannot mess up. It says that the ionizing radiation coming out of a decay, alpha, beta, or gamma, can happen in any direction. This direction cannot be predicted from earlier. So it is possible that these radiations can go in any way. The number 1 and number 2 can be slightly confusing. Let me elaborate this. The first one says, within a certain duration of time, the exact number of decays cannot be predicted. Within a certain duration of time, the exact number of decays cannot be predicted. This is why we have zigzag lines in the graph. Sometimes we have a bit high, sometimes we have a bit low. But if we draw the base straight line, then we get the half-life curve. The actual experiment never gives us a smooth curve. It gives us a zigzag up and down line. So that's the first thing. Within a certain duration of time, exactly how many decays will happen cannot be predicted. And the second aspect is that if we determine and if we pick off one specific undecayed nucleus and look at it and try to guess that this nucleus is going to decay after this many seconds, or after this many microseconds, or after this many years, or after this many centuries, we cannot do that prediction either. Within the whole undecayed sample, or within the whole sample, all the undecayed nuclei that we have, any of these nucleus could decay at any time. This is absolutely random. So for a specific nucleus, you cannot specify exactly when that nucleus will decay. You cannot do that. There is no order to this. There is no prediction to this. So the second description is about for one nucleus, and the first one is for a duration of time. Difference বুঝা গেছে কিনা বলবান?
Yes, sir.
আচ্ছা, এই জিনিসটা এখানে একটা জিনিস লেখা আছে alpha beta gamma are ionizing radiations not radioactive. What this means is that we call certain atoms to be radioactive which are unstable, and by undergoing nuclear decay process they emit alpha beta gamma. Alpha beta gamma are not radioactive, which means they are not going to break down into something else, something that can break down and emit ionizing radiation, which means something that will break down into smaller pieces, or no, maybe not break down into smaller pieces, they will have the same similar size, slightly smaller, but they will give up alpha radiation, get beta radiation, or gamma radiation, or maybe all three of them, or maybe two of them simultaneously. The source from which alpha beta gamma comes out, they are the radioactive nuclei. Alpha beta gamma are not radioactive. They are not going to undergo further breakdown. They are ionizing, which means whenever they're going to travel through a certain medium, they're going to do some separation of positive and negative charges. So that's that. How does that ionization happen? This is described very detailed over here. That whenever the ionizing particle, alpha beta or gamma, passes through a physical medium, it collides with the atoms and shares or gives up a small fraction of its kinetic energy to the collided atoms. The electron which receives this energy can become free of that atom, producing one free electron and one positively charged particle. That separation is what we call ionization. And because the incoming ionizing radiation, alpha, beta, or gamma, practically has quite a good amount of kinetic energy for atomic level, not for physical level. For atomic level, they have quite a huge amount of kinetic energy, so they can do a significantly large number of ionization. Now, the interesting thing is that alpha particles have a very small range, which means all the ionization they're going to do are going to be stuck within a very small location. Beta radiations have a bit less penetrating, bit more penetrating power than alpha, so their ionization would be spread over a long distance. Whereas gamma has the highest penetrability, which means gamma will practically try to penetrate through any thickness of material. If we want to stop a gamma radiation, we have to have very thick and very dense material like lead or something like that. So in terms of ionizing power, alpha has the most ionizing power within a small location, very concentrated ionization. Beta has a bit less ionizing power, and gamma has the least ionizing power. And because of this thing, alpha radiations are considered to be the most hazardous. They have the potential capability to give rise to the most amount of ionization within a small space of human skin or human tissue, which could lead to tumor or cancer. Betas can also do that, gammas can also do that, but the likelihood of achieving a cancerous cell or a mutated gene in the gene sequence, in the DNA sequence, is more likely to happen from an alpha radiation compared to a beta radiation and compared to a gamma radiation. এই আইডিয়াটা বুঝা গেছে কিনা?
জি স্যার।
আচ্ছা, এরপরে জিনিসটা সেটা হচ্ছে কোয়ার্ক মডেল। এখানে তোমাদের একটা জিনিস লেখা লাগবে, এটা আমি সবসময় কনফিউজ হয়ে যেতে লিখি নাই। দাঁড়াও, ওকে, এখানে একটা জিনিস লিখো। লিখো, এই নোটটাতে একটা জিনিস লিখো, কোয়ার্কস এক্সপেরিয়েন্স বোথ স্ট্রং অ্যান্ড উইক নিউক্লিয়ার ফোর্স। লিখো এখানে, কোয়ার্কস এক্সপেরিয়েন্স বোথ স্ট্রং অ্যান্ড উইক নিউক্লিয়ার ফোর্স। তারপর লিখো, leptons experience only weak nuclear force. তাই তো দেখলাম, তাই না? হ্যাঁ, আচ্ছা, এই পর্যন্ত আজকে থাক, আমি এরপর ফার্দার অগ্রসর হচ্ছি না। আই হ্যাভ টু গো টু আ পোস্ট ফিউনারাল প্রোগ্রাম। সো আজকে এই পর্যন্ত থাক। তোমাদের সাথে এরপর ক্লাস কি কালকে না?
জি স্যার।
ঠিক আছে, কালকে ইনশাআল্লাহ আবার দেখা হবে। তোমরা প্লিজ ইলেকট্রিসিটি ওয়ার্কশিটের বাকি প্রবলেমগুলো অ্যাটেন্ড করতে থাকো, ডোন্ট সিট আইডল, এন্ড ইফ ইউ হ্যাভ এনি প্রবলেম ইউ ক্যান পোস্ট দেম ইন দ্য নেক্সট ক্লাস অ্যাজ ওয়েল, যে স্যার এই প্রবলেমগুলো হয়েছে, এগুলো পাই নাই, দেখা দেন, আমি দেখাই দিব। থ্যাংক ইউ,
আচ্ছা,
আল্লাহ হাফিজ।
কালকে কি ক্লাস 5:30 নাকি 9:30?
কালকে ক্লাস 9:30টায়, না কালকে ক্লাস 5:30টায়, শুক্রবার দিন হচ্ছে 9:30টায়, কালকে 5:30টায়, ঠিক আছে।
জি স্যার।